So the next talk is by Ognjen Maric. The title of the talk is Cutoff Bounds for Consensus Algorithm.
Okay, thanks. So this is work done as part of my PhD at ETH Zurich. I'm currently at Digital Assets, still doing CAV, so big thanks to them for letting me come here. This is joint work with my supervisors at ETH, Christoph Sprenger, who's actually here, so if you mind just saying hi, and also David Basin. So one of key techniques for providing fault tolerance in distributed systems is replication. So you have a system, you replicate it, so that if one of the nodes in the system fails, the other ones can still provide the service. And now if you have a replicated system, what you almost always want is that all the replicas see the inputs in the same order. Why is this the case? Well, let's flip the order of one of the replicas. And now let's assume that this was an airline booking system, for instance. And if X was Alice's request to buy a ticket, and Y was Bob's request to buy the same ticket, well, you've just sold the same ticket to two different people, and if this happened to be the last ticket for a flight, one of them is probably going to be very unimpressed. And your system is going to be inconsistent, which means that it behaves differently from its ideal version, which is the centralized system. Okay, so now hopefully I've convinced you that it's a good thing to have. So the same ordering of inputs. And this problem of agreeing on the same order of inputs at all the replicas is known as the total order broadcast problem. And you can solve it in a simple way by solving a simpler problem, which is just simply let's all agree on what the first input is going to be, what the second input is going to be, and so on. So this simple problem of agreeing on one value is known as the consensus problem. So in a little bit more detail, in consensus, each replica has a candidate input, for instance, for the first slot in the order stream. And then they run this consensus algorithms, and what comes out is a single input value. So it should be the same value at all the replicas. Now, this problem is actually fairly difficult to solve. And the reason is we have concurrency, but what's worse, you have node failures because you want to be fault tolerant. You also have communication failures. And this actually renders the problem impossible to solve in general. So there's this famous FLP result about impossibility. And there's actually a whole slew of impossibility results. So if you like this kind of thing, there's like CAV theorem, impossibility of fair contract signing, all related to this. Okay, but if you do have some environment assumptions, you can still solve the problem. And we were actually developing a consensus algorithm of our own a couple of years ago. And the process looks a little bit like this. You start to develop an algorithm, and it's great. It has all these great properties. And then you realize, oh, my God, there's a scenario that I forgot where you have these three processes, and this fails, and so on. Just the whole thing just blows up. So, okay, you go on and fix that. But what then happens, you find another problem with these four processes. Things blow up again, and you iterate a few times, and well, finally reach something that works. You're very happy. But then you look back at all of these failed examples, you go, in all of them, I only needed a small number of nodes to actually trigger the problems. And you sort of wonder, is there something more to it? And then we learned that there's a whole body of work and standard terminology for these things. So what we have on our hands is first, it's a parameterized system where the number of nodes is a parameter to the algorithm. So your algorithm should work for 2, 3, 4, however many nodes. And what people have noticed before is that if you have a parameterized system, if you can prove it correct for small numbers of nodes, say, let's say 2, 3, 4, it tends to work also for a large number of nodes. So this is the small scope hypothesis. So what we set off to do is basically to prove this hypothesis. So we want to derive a cutoff bound such that if you verify your system with node counts less than the cutoff bound, you automatically get the correctness of the system for arbitrary parameter values. Now, this has been done in different settings before, but never for fault tolerance algorithms of this kind, and in particular never for consensus. So to derive these cutoff bounds, we first need some kind of some class of algorithms. And for that, we define a consensus language, console, which targets algorithms for the asynchronous setting with benign failures, so we don't consider Byzantine failures. And then we prove the small scope hypothesis for this. So we do this in 2 steps. First, we prove that a console algorithm is correct if and only if it's correct when you run it on binary inputs, so zeros and ones. And we call this the 0-1 principle because there exists an analogous result for sorting networks of the same name. And then we prove the cutoff bounds for this binary version of the problem. And what we get out, the bounds that we get are actually fairly small, so we get 5 or 7 for our case studies. And this actually gives you the first fully automated verification procedure for consensus. So in the rest of the talk, I'm going to cover, well, I'm mostly going to focus on the language to show you what you can express, and then just touch on the other parts briefly, so the 0-1 principle, the cutoff bounds, and the verification. Okay, so let's start with the language. So the language exploits some structural characteristics of consensus algorithms for our target settings, and I'm going to highlight these using the example of 1/3 rule, a simple consensus algorithm. So in this algorithm, all the processes run the same code, and the state of each process has an input variable, a decision variable, which is initially bottom, so nothing, and has this variable r, which you call the round variable. Why? Well, because this algorithm has this round structure where you have this big loop, and you increment r at the end of each iteration. So for those of you who are experts in distributed systems, I just want to stress that this has nothing to do with synchrony assumptions. It's just a structural characteristic of the algorithm. And now furthermore, a typical thing to do is to subdivide this round into the following phases or parts. So in the first part, you just send around messages. In this case, you send the value of your input field, tagged with your current round number. Then you collect the round messages. And what I want to highlight here is 2 things. So first, you collect the messages into a multiset, which means that you don't really care where they come from. You just care about their numbers. And the second thing is this if condition, which checks that the messages that you actually receive are from the same round that you're running. So in particular, all late messages are going to get dropped. Early messages, you might drop them, but what you normally do is you buffer them. So this ensures that the algorithm is what's called communication closed. Okay, and then based on these collected messages, you're going to update the state. I'll describe this in a minute. But this basic structure of rounds with these subparts is what's actually present in many consensus algorithms, and it was noticed before by Ali Gaffney and Sharon Boston Shipper also in their model called the Herdov model. It's a very nice model, so if you need to verify consensus algorithms, I suggest you look at them, at this model. Okay, and now the idea is that we remove all these parts that are common to the algorithms and just take kind of the differences. So what are we going to factor out first is this round structure. We're going to assume that it's there. Code is going to be run by all the processes. You're going to have the input and decision fields, maybe some other ones, but at least these 2, and they're going to be initialized in this way. And now let's look at these other subparts, what's left. So in sending messages, we always assume that they're tagged with the current round number. The only things you can change are what you send, so which fields or which field values, and to whom you send. Here it's to all processes. The collection, we actually assume that it's always looks like this, so you cannot change this. And now let's look at the updates. So here are the updates for 1/3 rule. The first update says, check whether I have received messages from more than 2/3 of the other processes. Remember, RP is this multiset of received messages. Now, this is very typical of all fault-tolerant algorithms because you won't receive messages from everybody, just from a certain fraction of processes. And then you further check whether all the received messages are the same. If they are, if they equal some v, then you store this v into your decision field. And there's another update of the input field, which has a similar threshold condition. And then you look at the most often received values, and you select the smallest such value, and you put it into input. Okay, so what we're going to assume is that the updates are always guarded like this. What can vary is this fraction of processes that you expect to receive messages from, and this selection predicate that you use to actually choose the value that you're going to store. So essentially what's left of the algorithm is this. And now we're just going to introduce some syntax. So this means all-to-all communication. This is basically an update with the guard to the left of the little arrow or triangle, and the same for the second update. And this is the whole thing. So this is a description of a round in console. Now your algorithm can actually have several such descriptions, so it can consist of several types of rounds. But each round description has to look like this. Now this is very minimal, but it's actually surprisingly useful. So you can use it to encode a large number or model a large number of consensus algorithms for our setting. Okay, so this is the language, more or less. So let's do some more sketches of proofs. Let's start with the 0-1 principle. So we're going to prove this by contraposition in a way. So if we have a multi-valued counterexample, we're going to convert it into a binary counterexample. So what does a counterexample look like? Well, you have states with a certain number of nodes. You run your algorithm for some k rounds, and then one process decides on an x, and another process decides on a y that's different from an x. Now, these decisions could happen in different rounds, but for simplicity, we assume that they happen in the same round. Okay, now we want to binarize this. How do we do this? Well, the first step is kind of obvious. Two values are sufficient for disagreement, so if you could replace x and y by 0 and 1 in some way, then you would get disagreement. But the question is, why would they do this? And for that, we look back at our algorithm, and we actually notice something. And that's that in this algorithm, values are always propagated between the processes. You never compute new values. And this actually makes perfect sense, because consensus is about agreeing on one of the inputs. It's not about computing new things. Okay, so then you can ask, why did they decide these things? Well, it's because they must have received it in the previous round from the network. So in the previous round, some of these processes must have sent a 0, some of them must have sent a 1, and then what we show is that you can, sort of simulation argument, that you can distribute zeros and ones among the processes such that these steps are possible. And then, of course, you need to answer, why did these processes send zeros and ones? Well, because they received it from somebody else in the previous round, who received it from somebody else in the previous round, and you get to an initial state where all the inputs are binary. So this is just a high-level overview of the thing. So the details are unfortunately pretty hairy. We also need some, fortunately, syntactic restrictions on console, but there are also, in the paper, there are also some examples where things don't go so well and why we need these restrictions. Okay, so we have our 0-1 principle. Let's do cutoff bounds. So we have the binary counterexample, but the problem here is that it could be large. So there could be a lot of processes involved, and we want to compress this. So how do we do this? Well, we look back at our algorithm, and we look at these fractions that appear in the algorithm's guards. And what we do is we take the least common denominator of these fractions. In this case, it's 3. And then we sort of create a ruler, if you want, where the notches on the ruler are 0, 1 over LCD, 2 over LCD, and so on. And we use this to measure the states in our counterexample. So here we see that we have, for both blue and yellow values, we have strictly more than 1/3 of the processes holding these values, but less than or not more than 2/3. And we do the same thing for this one. We can measure this state. And the idea is to sort of use this as your abstract domain, if you will. So we again run a simulation argument where we say that we produce a small counterexample where the states at the same positions in the small and large counterexamples are actually, they have the same measures in this sense. And now the question is, well, how small can you go while still preserving the same measure? And the answer that we come up with is that B, which is 2 times LCD plus 1, LCD is this least common denominator of the fractions. So there it was 3, and this example, the cutoff bound is 7. This is a cutoff bound for consensus properties of console algorithms. Now, again, the details are bit hairy. There are, again, some syntactic restrictions, so this result is model of those restrictions, but I won't actually describe them here. Okay, so now with this in hand, we have our cutoff bounds, and we can actually do verification. So we have a simple tool that takes the console algorithm. It just produces a Promel model of the appropriate size, so with the appropriate number of processes, the cutoff bound. It does some clever tricks, but nothing too clever. And then you just run spin on it, and you get your answer for verification. Now, actually, if you want to do verification of consensus algorithms, today you don't have too much choice. So you can do straight on model checking, which has the disadvantage of not being parametric, obviously. You can do, there's a paper at VMKI 14 which describes a consensus logic and a procedure for checking, for invariant checking for this logic, which means that it's semi-automated because you need to provide invariance. Also, the main decision procedure is a semi-decision procedure, so it's not complete. On the other hand, our main weakness is expressiveness. Okay, so we have the obligatory CAV table. But the takeaway here is just that we can actually verify some algorithms, and the times that we get are fairly reasonable, so on the order of a second or less. Okay, so just quickly, what are the open questions? Well, like I said, we have complicated proofs. It would be really nice to find some simpler ones. I believe that simpler ones exist, maybe by connecting things to a logic like Viktor Kunčak's BAPA, or actually this consensus logic or something like that. But I don't know how to do this. Maybe you do. Then you could do both parts together or separately. If you do zero-on principle, then there's a line of work by Igor Konov and other people, and this might help extend this work to consensus algorithms. We also actually don't know anything, as far as I know, about undecidability bounds for verification for such systems. And a straight-on also extension would be to extend this to different algorithms, such as this total order broadcast or Byzantine setting and so on. Okay, so that's all that I had. Happy to take questions.
Questions?
So does this extend to liveness properties, the cutoff bound?
So we do, we actually only look at the consensus properties. One of them is termination, which is the liveness property. So, but we don't have a class of properties. We look at the 4 consensus properties. But one of them is the liveness property, yes.
Just a quick one. What is the most important restriction of your framework where it would break down and you need more work to extend it?
So one thing that we need is sort of that these guards are ordered. So all the guards, the selections that appear in your in the algorithm have to be strictly ordered in some fashion. So they have to be stronger than each other. For instance, that's a big restriction. But there was a couple of other ones.
I just have a small question.
Yeah.
About your specification language. Are you happy with that, or are there some extensions that you like to?
I mean, the language, so right now we have a pre-baked set of predicates. It'd be nice to get like a syntactic class for these things. I'm not sure if it's super useful, but it'd be nice to get. And I think the base language is mostly okay. It's just that the restrictions that are really annoying. So.
Okay, thank you.
Thank you.
Thank you.